Hello, I'm Lilli Thompson, and this is Console to Chrome, HTML5 and JavaScript for game developers. So first of all, just a little bit of background on me. So I am an ex-console game programmer that joined Google as a software engineer, and I did that for a couple of years. Nothing to do with graphics or game, just generic software engineering. And then I found that I really missed game development. So I then joined the Chrome team as a game developer advocate. And what that means is that what I do now is that I work with game developers who are working with technologies that are a priority for Chrome. And the big two for me are HTML5 and WebGL. So that's what I do a lot of, and that's why I'm here today. So first of all, like an overview of this talk. The thing you really need to know is that this is a 201 level talk. I'm not going to give you the HTML5 pitch, and I'm not going to give you an intro to game development. I'm going to assume that you're a game developer type person that already knows that they want to use HTML5. Maybe you've done a WebGL tutorial and even rendered your first couple of triangles. But now there's a huge knowledge gap between making a prototype and actually making a scalable, large-scale game engine. And so that's really what I want to address today. And there are a couple of topics that go into that. The first, I'll just have to go really briefly over the HTML5 APIs. I'm not going to spend a lot of time on it, but I want to make sure that we're all on the same page. Then, the real meat of the issue for a lot of game developers is JavaScript. Just writing code at that scale in JavaScript is something that a lot of console game programmers struggle with, and so I'm going to spend a lot of time there and talking about how to do that. And then finally, when you write an HTML5 game, you're actually writing a game that renders inside a much more complicated system of Chrome's rendering system. And so there's all sorts of things to know there, and if you really understand how Chrome is set up, you can optimize your game and make it run better. So those are the topics I'm going to cover today. So there are two major ways that people think about HTML5 games. The first is as a means to get ubiquity. There's a whole class of people who look at HTML5 as a way to write one code base and run it in multiple places. So the dream is that, every phone, every tablet, every PC, every device has a browser. And if you can squish your game into a browser, into HTML5, then that's great for your maintenance. You have one code base and it's running everywhere. That's awesome. But that particular use of HTML5 comes with a certain set of constraints. So naturally, if you're really targeting ubiquity, if that's your point, then you have to peg the specification for your game to the lowest common denominator. And both in terms of what APIs you can use, because you need APIs that are very broadly supported, and also in terms of what you can demand out of the hardware, because you have to assume that you want to run just as well on a phone as you do on a desktop. So anyway, very nice use of HTML5, but then there's this other way people think about it, which is as a way to do something awesome with a browser. So there's a different set of people who see the browser as a distribution platform for their console-style games and are really excited by all the great new potential that HTML5 has added to the browser, and they really want to take advantage of that. And there's a huge potential there, making shareable, linkable, seamless experiences. You can get so many users that way, and it's so exciting. But as you can imagine, these people who are really interested in being on the leading edge, their goals are very different than the people who are trying to do HTML5 for ubiquity. Because by virtue of being on the bleeding edge, these things aren't going to be supported everywhere. If you're making a game that's a PC-style game that's really demanding, it's not going to run on 10-year-old hardware. And that's OK for this use case. So when you ever you talk to people about their opinions about HTML5 and what it's good for and what it isn't good for, you should make sure you understand which of these cases they're coming at it from. And to be very clear here, what I want to talk about today is the leading edge of HTML5. I want to talk about credible console-style experiences rendered in the browser. All right, so begin talking about that. We need to talk about HTML5 APIs, at least briefly. So the first one you're going to need is WebGL. So WebGL is the way you do 3D rendering in a browser. It's a lot like OpenGL, so if you're already an OpenGL programmer, it's going to be pretty familiar to you. Except for, it's actually OpenGL ES 2.0. It's the embedded systems version of OpenGL. And what that means is that when they made the embedded systems versions of the specifications, they took out everything that was deemed to be redundant in order to make it small and compact to fit on mobile devices. But that means that a lot of stuff is sort of removed. And the first thing you're going to notice there is that fixed function lighting is gone. So all your rendering in WebGL is going to be done through programmable shaders. You're going to have to get used to that if you're not used to that already. And besides that, there are a bunch of other little things which, when I talk to game developers about them, they're usually described as annoyances. Just random stuff that just is missing for whatever reason in the specification. So for instance, depth buffer access, texture compression is only available in a limited form, instancing is missing, and so on and so forth. So there are little stumbling blocks. None of them are deal breakers. You can still make a high quality, graphically impressive 3D game, but you're going to have to know that these issues are there. And then there's a different class of things, which is a set of operations in OpenGL that have a different performance profile than you might expect in Chrome. So for instance, anything that starts with a read, anything that starts with a get, and GL finish, that kind of operation, they're all going to be extra expensive in Chrome. They were always somewhat expensive. Now they're going to be really expensive. And when we get into talking about how Chrome actually renders things, I'll be able to explain why that is. But besides those performance sort of notes, the rest of the performance of WebGL is actually pretty great. It's actually tremendously impressive. It's really calling straight through the hardware, so the performance of WebGL is very, very similar to the performance of OpenGL, and you can get a lot out of it. And the other thing to note is that the specification is evolving very, very quickly. If you look at where WebGL was a year ago versus where it is today, you're going to see a lot of improvements. So especially when you think about all these little things that are either annoying or missing or whatever, make sure you check back in with your assumptions every 3 to 6 months, because fixes very well might have come into the specification. Or better still, go to the WebGL mailing list and start talking about what it is you need and want, because they're very responsive and a lot of changes are getting made. All right, so you can render polygons. Next thing you need to do on your way to a prototype is be able to play some audio. HTML5 audio is a notorious sticking point. Everyone in the HTML5 games community has heard everybody else complain about how painful audio is, and that's pretty true, quite honestly. It's pretty safe to say that audio in HTML5 is the most important, least standardized thing. So there actually is no specification that's really suitable for this kind of game that's going to work everywhere. So you're stuck sort of falling back and doing different things for different browsers. I wish it wasn't the case, but that's sort of the world we live in today. Of all the specifications out there, the one that I personally think is the best and most suitable for games is the Web Audio API, which is only in Chrome right now. And it offers just a lot of features, sort of a graph-based audio processing system, all kinds of out-of-the-box nodes and filters you can just use. It's hardware accelerated, it's very accurate in its timing, and so on and so forth. So it'll help you out. And then there's so much more that I just don't have time to get to today. There's all kinds of new APIs being added to the HTML5 standards all the time. Instead of trying to go over them here, because I just don't have time, I'm going to add a resources slide at the end where you can go and read about any one of these particular things. There are also lots of presentations that sort of catalog APIs for games. But suffice to say, for the moment, there are a lot of things that you should look into. If these things don't look familiar to you yet, then you should go look them up and see if they're useful to you. And that's pretty much it for HTML5. Pretty much two things you need. You need to be able to render triangles. You need to be able to play sound. From there, you can make a prototype. Once you've got a prototype, now comes the hard part, where you take prototype to game engine. And that transition is all about writing high-performance JavaScript. So that's what we're going to talk about now. And before I get too deep into it, a great big caveat that what I'm talking about is JavaScript performance for Chrome. Every browser has its own JavaScript engine, or there are many different JavaScript implementations, and they're all going to have different performance quirks. Certain operations are going to be slow over here and fast over there and all that. So this presentation, I'm going to try to give you general information, but this information has been written in the context of V8 and sort of confirmed with the V8 team for accuracy, and I'm not trying to or qualified to speak for other browsers. All right, so let's talk JavaScript. JavaScript is a sort of high-level scripting language, and it's extremely permissive in what it allows you to do, extremely squishy in its syntax. It's typeless, it's kind of interpreted, it's just-in-time compiled. There's no explicit syntax for memory management, and it's all running on a single thread, with some HTML5 exceptions called web workers, which you should go look up if you don't know what they are already. So the nice thing about JavaScript is that it's great to have an application running in JavaScript in front of your end users, because it is great at not falling down. JavaScript is great at eating bad input and staying up. Nothing makes it crash. It's super effective at being robust. The sort of dark side of that, though, is that because JavaScript doesn't have a lot of structure of its own, and because it is really, really permissive in what it allows you to do, and it never sort of spits errors at you, that while you're developing, you're sort of stuck in this Wild West kind of lawless world, and it's really hard to work in that kind of unstructured environment. So what from a developer standpoint, what I usually think is that you want a really permissive system for deployment because you don't want to put something in front of end users that will crash, and you want a really strict system for development so that JavaScript doesn't allow you to do anything silly. And JavaScript being way over on the permissive end of the spectrum, development of large-scale systems in it can be difficult. So what people do, because JavaScript doesn't bring a lot of structure of its own, is that they impose artificial structure on JavaScript. So either they have their team follow very strict coding standards, or there are patterns that allow you to privatize data. Even though JavaScript doesn't have an actual way to privatize data, you can sort of fake it with certain patterns. There are post-processing tools that will warn you or add static types and tell you when you're doing something silly. So there's all that kind of stuff that you should be aware of if you're making a large-scale JavaScript application. And then you should also just be aware that JavaScript is not going to spit a lot of errors at you. So when there are problems in a certain part of your system, it might be hard to figure out what exactly has gone wrong, because JavaScript always thinks that everything is OK. So it's hard to trace back error chains. And in an environment like that, you want to code extra defensively. The idea is that you want to design your system in a modular way, which is always a good idea. And then hopefully you can design it such that if one of your modules starts behaving strangely, starts going wonky, and you can't figure out why, you could just kill it and restart a fresh one and reconnect it to your system while the whole thing is running. And if you can design in that way, you'll save yourself a lot of pain dealing in the system this sort of squishy. All right, so if you're still one of those people who thinks to themselves, well, JavaScript, that's a scripting language. You could never actually write a high-performance, sort of credible game in JavaScript. You are dealing with seriously dated information. JavaScript engines are really fast these days. They are absolutely capable of doing the kind of processing required for this kind of game. The problem is that it's just really easy to write bad code in JavaScript. And there are a ton of examples of bad code in JavaScript that people tend to follow as patterns. So not only is JavaScript performance sort of squirrely in that it's hard to tell what exactly is going wrong, or small changes in your JavaScript can have really, really big performance implications, and that information isn't really surfaced all that well to you as a developer. But on top of all that, the VM itself, the actual virtual machine that's executing your JavaScript, V8 in Chrome's case, is under development too. So something that was slow yesterday might be fast today. And so you have to sort of keep all of this in your mind as you're trying to write high-performance JavaScript. So the best way I know how to give advice on how to write high-performance JavaScript is to sort of explain to you the pieces, the general components of how V8 is actually executing things, and then you can develop an intuition for what might be fast and what might be slow and go from there. So again, I'm talking about components of V8 here. In general, these are components you find in a lot of JavaScript engines, but this in particular is referencing V8's implementation. So the components are, you have a just-in-time compiler. That compiler compiles to some representation, so you have an object model under the hood. You have an optimizing compiler that compiles after that, and then at the end of the day, you have a garbage collector that's running around cleaning up after you. So I'll talk about each of these components. First of all, the just-in-time compiler. So the just-in-time compiler, what it does is very easy to explain. It looks at the JavaScript you wrote, and it takes snippets of your JavaScript, and it turns them into native code. And that translation, the directive of the just-in-time compiler, is to do that as quickly as possible. It doesn't try to be overly clever or to sort of specialize or optimize at that point. It's trying to make the interpretation of JavaScript files fast, so it just does that translation as fast as it can. And it does a great job of it. So when we talk about the just-in-time compiler, we're talking about generating native code. So now we need to talk about what kind of native code gets generated. So we need to talk about data types. So the first data type of interest is numbers, numeric types, of course, very important. So V8 has two major internal representations of numbers. There are small int values and heap numbers, and they have different performance profiles. So small ints are the case you want to be in if you can. They are immediate values, as opposed to heap numbers, which are allocated somewhere else on the heap. Small ints are something you're just holding on to, and that means they're really fast to interact with. Heap numbers, the size of a heap number is sort of an interesting question. On 32-bit machines, heap numbers are ints that are less than, or 31 bits or less. On 64-bit machines, small ints are 32 bits or less. So there's some sort of intricacy there. In general, you probably want to target both 32-bit machines and 64-bit machines. So you probably want to aim for 31-bit integers if you can. Now, don't go crazy with this, because other kinds of numbers can be optimized later too. But if you have a system, like your octree system or your particle system, that lends itself to being cast in terms of integer math, it might be a major performance improvement for you if you can get into these SMI values. So that's SMIs. Then we have heap numbers. So heap numbers are anything that won't fit into an SMI or is not a local variable. So exactly like you'd expect, these numbers can't be allocated in immediate mode, so they need to be wrapped up and allocated on the heap, which means that now they're going to be slightly slower to deal with because you're referencing a number that's somewhere else. Now, before you go crazy, again, I want to make sure that I don't accidentally tell you to over-specialize. Doubles are sometimes optimized. V8 knows that math is really important. It's something people want to do a lot of. So it will try to optimize your doubles. It'll try to allocate them in immediate mode. It'll try to allocate them in registers if it can. But it might not be able to, so there's no guarantee there. So again, don't go crazy trying to make all small ints, but if you can, if it lends itself to your system, it could work for you. All right, so that's numbers. Next, we need to talk about arrays. So the first type of array to talk about in JavaScript is the typed array. So typed arrays are going to make a lot of sense to you if you're coming from a C background. They are contiguous blocks of memory that are specified for a particular data type. So you have uint32 array, float64 array, uint8 array, and so on and so forth. Which actually, if you're familiar with JavaScript, is sort of unusual, because most things in JavaScript have no types. So this idea that we're specifying a very specific size for our numbers is actually pretty unique. And that's because the typed array specification grew up alongside the WebGL specification. And you can imagine how you need that level of specificity if you're doing graphics programming. So that's sort of where the typed array specification came from. But it's sort of been adopted into other things now that it's there. So again, they're memory efficient. You don't have to box them. They behave as you'd expect. They're a very nice option for arrays. But if you can't use typed arrays for whatever reason, you need to use JavaScript arrays. So JavaScript array object, array with a capital A, has an API which is going to look a little weird to you if you are used to C-style arrays. It's going to have operations that are different. It's going to have like push and pop. It's going to allow you to index out of bounds. It's going to have just sort of odd behavior to me as somebody coming from C. So as you can imagine, because the API allows all these non-C array-like things, the backing storage in V8 is not always something that looks like an array. There are actually two different types of backing storage for arrays. There are sparse arrays and dense arrays, which map to either something that looks like a C-style array, like you'd expect, or a hash table. And if your array is backed by a V8 hash table, that's called being in dictionary mode, and it's considerably less efficient. It's a case that you want to avoid. V8 there are many factors in V8 that causes you to be kicked into dictionary mode or not. So it's kind of complicated to define them all, but one of them, for instance, is space efficiency. So if the code you wrote would be 3 times more efficient, use 3 times less space if it was backed by a hash table than an array, then it'll be a hash table on the back end. So there are criteria like that. Let me give you an example. So this is something that JavaScript allows you to do. JavaScript allows you to create a new uninitialized array and then just suddenly index into it at some whatever index. This, of course, doesn't make any sense in C. It's not something you'd actually do. And in V8, it will immediately trigger dictionary mode. So this, you will now have a nice, slow array to work with. Not something you want. This is an example of a better way to do things. So real simple change. All you have to do is declare how much storage you want up front. Now you have declared to V8 that you actually want an array of a certain size. V8 will back your array by a contiguous array of that size, and you can go from there. Very sensible, kind of no-brainer-ish, but again, JavaScript allows you to do it in a way that ends up being very inefficient, so it's important to know. All right, so that is the numeric representation and the sort of immediate representation of objects. Now we're going to talk about representing JavaScript objects in V8. So objects in JavaScript are these very poorly defined things. They are associative arrays. They're just bundles of key value pairs of properties. So you have string value for key, property value. And all property values are sort of these undefined, whatevers, because JavaScript doesn't have a notion of type. Objects have prototype chains. You can add and remove properties anywhere at the prototype chain and on the object itself at any point. JavaScript doesn't enforce any sort of specificity or structure in your code. So if you wanted to, you could make every single object in your whole program absolutely a unique set of properties. Nothing in JavaScript will enforce structure or self-similarity. But just because JavaScript allows you to do that, you really, really shouldn't. That's actually a terrible thing to do for performance, and I'll explain why in a minute. So in V8, the V8 team looked at trying to write a large-scale application in JavaScript and thought, hey, you know what's important in large-scale systems is object-orientedness. And if you have object-orientedness in your system, then now property access is one of the key things that you need to make fast. So V8 sort of designed its structure to make property access on objects as efficient as it could be. So the internal representation of an object in V8 is 3 words. So first we have a hidden class pointer, which is sort of an internal notion of type, which I'll explain in a second. And then we have 2 pointers to different kinds of properties. We have properties that have string names, and then properties that have int names. But really, the only thing that's important is you have a type, and then you have property storage. So what's this hidden class thing? So hidden classes, again, they're V8's internal notion of type. JavaScript itself isn't going to enforce any kind of notion of type on you. But in order to make things efficient, V8 itself needs to have some sort of structure in what it thinks you're doing. So it introduces a type system. And that type system sort of groups objects with the same structure. So as you're adding properties to objects, which you can do in JavaScript, V8 will be looking at the properties on each object and mapping that bundle of properties to a hidden class which defines an object with exactly those properties. So for instance, if I have this constructor in JavaScript where I have a point and it has an x and y, and the way those values are added by first adding x to the object and then adding y, that's going to generate a hidden class that backs objects that are created from this function that has exactly the properties x and y. And that's really, seems sort of obvious, but then the first time this function is run, that hidden class is going to be built for the first time, and then all subsequent times this function is run, those new objects can share this same hidden class. So you only pay the price for building it the very first time. After that, you can just use the same object. So we went through all this trouble of building up a notion of type. So now we have types that correspond to specifically what exact properties are on an object. We can use that notion of type to make property access quickly using something called inline caching. So if you want to look up a property on an object in JavaScript, you're going to say, I am looking for property with name x on object y. The first time you do that, the first thing you do when you're trying to look up a property is check the hidden class of the object. If you've never tried to look up that property on an object of that type before, then what you're going to have to do is a fully generic search for that property. So again, we just have a bundle of properties somewhere. They all have string names. You have a string of the property you're looking for, and you're going to have to look through that list for the property that has a matching name. That's a pretty slow operation. But once you've found that property once, you can remember the offset to it. You can remember where you found that property and use it later, which means that you can use that to generate new optimized code which specifies how you look up that particular property on that particular object. And the next time you want to look up a property with that name on an object of that type, you can have direct access. You know exactly where to go in an object of that type, and it's much, much, much faster. So that's really what the notion of having a hidden class is getting us, is now we can make property access really fast through inline caching. So this is a classic example of a bad idea. So I have another constructor. It's sort of creating a vector object. It's adding an x and y. But then, after I go through the trouble of doing that, I decide that I now want a property z on this object. The problem with that is that if you add a property z to that object at some future point, if you just dynamically do that, you're going to change the hidden class of the object, which means that all this nice caching you've done and building up a notion of where the properties are, that's just blown away, because now you have a new hidden class. You have to pay to build a new hidden class, and now you have to deal with a new hidden class. So one of the best things you can do to make your code efficient is to create a few well-defined types. Don't do a lot of dynamic property adding and removing outside of constructors. Pretty much set things up once, have them look alike so that they can share the same hidden class, and don't mess with the properties they have. All right, so now we know an object has properties. Those properties can be in different storage states. So the first state, the default, is that they can be stored directly in an array on the object. That's great, that's fast, that's where you want to be. A second state they can be in is being stored in an array off the object. Still great, still an array, no problem. The third case, which is the one you really have to look out for, is when they're stored in a hash table. So much like just the array case in general, where arrays can have different types of backing storage, properties can have different types of backing storage too. So properties can either be in normal mode, where they're stored as an array, or in dictionary mode, where they're stored as a hash table. And if you have an object in dictionary mode, it's going to be much slower to interact with, so you don't want that. So what triggers dictionary mode, and how do you avoid it? Well, one thing that triggers it is too many properties. So if you have so many properties that they won't fit into the internal storage for properties, then you have to have a hash table elsewhere. And that number of too many properties is somewhere around 30. It's quite generous, but you might hit it in some cases. The other things you can do to confuse your object and kick it into dictionary mode are to change the properties on that object. You can change the attribute, you can delete properties, that kind of things. Those things are all going to kick you straight to dictionary mode again, and now you're going to make your object much slower to interact with. All right, so that's object storage, and we have a general idea of what we want to do, which is pretty much create repeating common sort of stable structures in our code, not change them too much so we can do all our nice caching and stuff. Now we're going to talk about the optimizing compiler, which is how you really make JavaScript fast. So the optimizing compiler is the second of two compilers. Remember, we had the just-in-time compiler first, which is doing its best to just make the translation from JavaScript to native code as fast as it can. And then we have this other compiler, the optimizing compiler, which is actually going to look at that code that's generated and try to make it really good, fast code. So because JavaScript doesn't give you any language to tell V8 what you're intending, the only thing that the optimizing compiler can do is sit back and watch your system as it warms up and try to infer structures in your code. It's going to watch what you're doing. It's going to watch for what types are where and how the data is flowing through it, and then make inferences about the kinds of optimizations that it can do. So this is a costly operation, which is why we don't actually just try to optimize everything. The system only tries to optimize functions that have been deemed to be worthwhile, and that decision is made from profiler threads. So when crankshaft, which is the name of V8's optimizing compiler, spins up a profiling thread to watch for what functions are hot. When it sees a function that it thinks should be optimized, it then looks at the type data it's collected so far. So it's like, this function seems to take ints all the time, and it seems to return this kind of data, and so on and so forth. And using that type data that it's collected, it can do all sorts of optimization. It can inline code, it can do loop invariant code motion, it can do all sorts of optimizations and specialize on those types. Then it can take the new optimized fast path code it generated, do on-stack replacement to just swap it out in place, hold on to the old slow code just in case it needs it later, and continue on executing without anybody knowing the difference, except for that the code is much, much faster now. So the optimizing compiler is really the heart of what will make your game JavaScript performant. And you really need to be working with this system to try to play nice with it. So what kinds of structures are optimized by Crankshaft? Well, I'll tell you, not everything. Not everything is an eligible construct in your JavaScript for optimization. When Crankshaft looks at a function, it's like, I want to optimize that. It starts trying to optimize the code, and then in the middle it hits something that it can't actually do. It finds something that it can't optimize. That's a condition we call a bailout. A bailout means I tried to optimize this, I tried for you, but actually I couldn't do it for some reason. So I'm just going to not try to optimize that. And there are a number of things that cause bailouts, and they actually change a good deal. So one thing is that functions are too long, that functions that are really, really long are not candidates for optimization. This is an interesting case because some of these tools that try to make your JavaScript fast, like post-processing tools like Clojure, Some of those, in some cases, do such aggressive inlining that they create these giant functions, and then those giant functions are no longer candidates for optimization by Crankshaft. And so they actually make the code a good deal slower. I've seen this happen. So just when I say function too long, you probably wouldn't write it, a function that long, but something that's post-processing your code might. So you should keep your eye on it. And other than that, there are just a number of specific cases that can't be optimized. If you want to see what's being optimized and what isn't, you can use these two handy V8 flags. You can use trace bailout and trace opt. Trace bailout will spit out the function names of what things are bailing out and why. Trace opt will tell you what functions are getting optimized. So I have a bunch of specific output from trace bailout. These actually came from a recent trace that I ran. And you can see this sort of makes sense. They're very readable, sort of try catch not supported, for in not supported, non-string to string not supported. I debated a lot putting them on the slide. I wanted to put something up here as representative, but just know that these are the types of things that will change. Like the V8 team is trying to optimize this. They're trying to handle more cases. So just keep checking in about what in your code is bailing out and what is working well, and keep watching with the flags. All right. So the thing is, all those wonderful optimizations that Crankshaft made for you when it does successfully optimize functions are speculative. They are based on the information that Crankshaft has at the time they are made. So again, the way Crankshaft works, it just watches the system, it sort of infers what patterns are where, it sees sort of what the types kind of are, and then it tries to specialize based on that. So if your code always did things a certain way, it always passed this function ints, and then suddenly it's like, nah, I want to pass this function objects or strings or whatever. Suddenly the assumptions that were made to optimize that code are violated. And that results in something called the deopt, which is where we have to take that slow code that we kept around just in case and swap it back in for the fast code. And deoptimizations are really tragic. They're sort of a double fail because you paid to optimize the code, which was expensive, then you paid to swap it in, and then you paid to swap it back out again, and now you're running slow code again on a function that Crankshaft thought it should optimize. So you really don't want deoptimizations. The way you tell whether your code is deopting is using another handy flag in V8, trace deopt. And that will, again, it'll tell you the names of the functions, it'll output them to stdout. The names of the functions are deopting and why. So keep an eye on that as you write your game. So in general, what you should be taking away from all this is that JavaScript, it's this wonderfully elegant dynamic language. So you can, once you get used to it, you can do all this stuff which is very JavaScripty. You can dynamically add properties and take optional arguments to functions and use closures in this very elegant way. Whenever you see something that's really dynamic and really JavaScripty, you should be a little bit suspicious, because just because you're not writing native code doesn't mean that someone isn't writing native code. Remember that Crankshaft is over here watching what you do and trying to figure out what you mean, trying to infer from your program's behavior what you mean. So if you keep changing what your program does, it can't help you optimize. So the more type stable and predictable and C-like you can make your code, the better you're going to be. So again, that's a sort of rule of thumb. Javascriptisms can be fast, but if you want like a hard and fast rule, the more like C it is, those things are likely to be faster. So in terms of other rules, so create a few well-defined object types. Don't add way too many properties to objects. Keep it reasonable. Don't start changing the data types your functions take. Sort of try to make things type stable and C-like. Don't use functions that are way too big. And in general, just as you develop, keep an eye on what's going on in V8. Profile occasionally with trace deopt, trace GC, trace bailout, and see what's going on, and just keep an eye. All right, now the last thing. We'll talk about the garbage collector. So JavaScript, of course, is a garbage collected language, and garbage collection hitches are one of the very first performance problems I hear people complaining about. When people write large-scale JavaScript systems, one of the first things they come back with is like, wow, we're getting this like sawtooth performance curve. What's up with that? And that's the garbage collector going. So V8's garbage collector is a precise incremental generational garbage collector. Of all those adjectives, the one you really need to care about is generational, which really just means there are two areas of memory things get or two or more. There are actually more, but 2 areas of memory for all intents and purposes. There's a small area that's for really short-lived objects, and then there's an area for objects that are going to live a long time. And if you want to see what's going on with the garbage collector, you can run, again, a handy-dandy V8 flag, trace GC, and that will spew a bunch of information about what's going on with the garbage collector for your perusal. So if you're trying to make an application that is garbage collector friendly, one of the things you should be aware of is that promotion is expensive. So again, we have a generational garbage collector, so we have a young generation and an older generation, and the promotion of objects from the young to the old generation is expensive. Because you're actually copying an object out of one area of memory into another area of memory. So one of the worst things you can do is you can have an object that lives just long enough to get promoted and then you forget about it. So you want, in general, either objects that are going to live a very short time or objects that are going to live a very long time. Medium-lived objects are you're kind of wasting some time promoting them. The other thing you need to be aware of is that, in a system that is garbage collected, it's very important that you release your references to things. Pretty obvious, except for that in JavaScript, it's you can have these large systems and it's sort of hard to tell what's going on. Also, there are some tricky things in JavaScript that can hold on to references for you. So for instance, execution contexts and closures can both hold on to references for objects and not let them get collected. So you need to be a little careful with your JavaScript. Keep track of where all your memory is. And then the number one thing you can do to sort of make a garbage collector friendly application is to not generate garbage. And that will help you avoid GC stalls. So the difficulty with that is that most things are objects in JavaScript. Temp variables, closures, all this other kind of stuff is JavaScript. Very few things aren't. Small ints, for instance, are one thing that is an immediate value. So that's another really good reason to use small ints. Other than that, good rules of thumb are to use scratch pads, sort of reuse variables for between functions, and to update things in place where you can. So for instance, this is an example of a classic bad idea. So it's just a simple vector add function. One of the first things you're going to need is a math library. You might think that this was a good way to write it, except for that this actually allocates a brand new vector object every time you try to do a vector add, which is going to be often. So that's going to be really, really garbage collector unfriendly. This is a much better way to write it. I actually much prefer the first syntax, but this is a much better way to write it in the context of a garbage collector, where you actually add to the first vector. You just update the first vector in place. You don't allocate a new object. So this is going to work a lot better. Subtle point here is that if you're working with doubles, again, you might be be boxing and allocating new heap numbers. So this might create some garbage collector pressure anyway, but it's still going to be much better. All right, so now you know how to write a high-performance JavaScript application, or hopefully you have some intuition as to what might be fast, what might be slow, and how to check whether things are going well or not in your JavaScript. That's awesome. Now we have to take that application and put it in Chrome, in the context of Chrome where all this other stuff is going on. So let's talk about that. So first of all, when you're in Chrome or when you're in any browser, it's just very different than being on a PC or a console. There's a lot of stuff you don't know. You don't know what browser you're in. And different browsers, they have different performance profiles for different operations, and also, they support different HTML5 APIs. So every single thing you do, you need to check whether it's supported here. You don't know anything about the local hardware, and this is a really hard one for people to get their head around how important this is. Most game developers who are coming from the console PC space have never had to deal with a range of hardware so broad as you have to for the web. There are everything from a 5-year-old phone to the latest and greatest desktop system of today. That's the range of things that can run HTML5. And so you can get these huge performance differences, which means that that it's very important that you do a lot of checking in your code about what the local system can handle. Another thing you have to know is that your game lives in a tab. What does that mean to you? It means that that tab can actually close at any time. Now this is always true. If you're writing a console game, the user can walk up and hit the power button on the console. That's always an issue, except for that the way people interact with tabs in a browser is far more ephemeral. It's very normal for somebody to be playing a web game and then be like, oh, I want to check email, and just close that tab down. And this is important for you to know because if you're writing files to local cache or something like that, you're going to have to be very careful that you're ready to be shut down at any time. There might be other applications running in your same thread. Here I'm talking about Chrome specifically. So you might not have the whole thread to work with. And there's this other compositing and rendering cycle that's going around your game that's making the whole web page itself. And so you need to fit into that as well. All right, so let's talk about this local hardware thing. So you know nothing about the local environment. And I know I just said this, but I really can't stress it enough. Because of privacy concerns, there's nothing in JavaScript that allows you to ask detailed questions about a user's local machine. So there's no way that you can ask, what kind of hardware is this? What can it support? So you're just in charge of being able to scale on your own. And in the PC world, this is not a problem because PC games, console games don't have this problem to begin with. PC games specifically say on them what the system requirements are. And everybody's used to that. Everybody's happy with that. On the web, people have this expectation that everything be lowest common denominator, which is a blessing and a curse. I love that you get broad distribution. However, it makes it really hard if you're trying to target the high end. And so what you can do about this is just be very, very clear with your users about how your game will run on their machine. The last thing you want is to have your users buy your game from some web app store, the Chrome Web Store, for instance, and try to play it and then find that it doesn't run or it runs at 5 FPS or whatever because they're running on very old hardware. And then they give you a 1-star review. They're like, this game sucks, I can't run it. So you really, really need to be communicating proactively with your users about what they can expect from your game. I can't stress that enough. It's really important for end user experience. Also, if you can, you want graceful degradation where it's not just a binary thing. You want to be able to make your game sort of gracefully scale down to fit on lower end hardware. So one thing you can do to that end is micro-benchmarking. And so this is where you yourself, again, it's all homebrew, nothing in the JavaScript standards helps you, but you yourself write little benchmarks that stress what your game is going to stress and collects data about that. So maybe during your loading screen, you run a bunch of tests, sort of get a feeling about what the local system is, and then suggest settings or send that data back to your servers for analysis. Or while the game is running, you see what the FPS is and sort of adjust accordingly or take data accordingly. But you really need to be proactive about collecting this data. And that's pretty much it for dealing with the hardware variation you're going to find in HTML5 games. It's collect data, communicate, and make sure, above all, that you set your users' expectations appropriately. All right. So up until now, I've been talking about HTML5 specifications. I've been talking about how to make JavaScript fast. Those things all live within V8. So here we're talking about things that live in V8. Let's talk about what goes around that. So V8 lives in WebKit alongside CSS and HTML. So the same way V8 executes JavaScript, there's another machine for HTML and another system for CSS. All of those things live side by side. When they want to render things, any one of those things can send commands on this RPC buffer to the GPU process. All rendering in Chrome is done in a separate process entirely, not just a separate thread, a separate process. And it's done on a separate process for security reasons. And so this structure is very important to understand because you're sharing this RPC buffer with everything else that's trying to render anything. Then from the GPU process, it'll actually communicate with the drivers and the hardware itself to do the actual rendering. But there are a couple of additional pieces of complexity here. One is that on Windows, where you don't have good OpenGL drivers, there's this layer called Angle, almost native graphics layer engine, and that will do a translation from OpenGL to DirectX. And then there's this other translation layer called Swift Shader. So on machines that don't have good drivers, or drivers that are good enough for WebGL, Swift Shader will actually do software rasterization. So there's all this complexity from your game on down into the actual rendering. So let's talk about that. So first, let's talk about the RPC buffer part. So if you remember way back when I was talking about WebGL, I mentioned that certain commands have unexpectedly slow performance. And those are anything that starts with read, anything that starts with get, these things that require round trips to the GPU. And now that you understand that there's an RPC buffer in there and rendering's done on a separate process, I'm hoping that you'll have some intuition for why that is and what sorts of commands might be slow. So besides that, you have to know, the other thing you have to know about that buffer is that it's shared and it's limited in size. So there's a specific size limit on that buffer, and all the resources that you upload to the GPU are going to eat up that size. And it's total size of resources, not total of number of resources, but all your textures, all your buffers, all your commands, they're all going to go into the budget for that buffer. And if you go over that buffer size, then you're going to trigger something called a sync flush, which is slow, and it's going to amount to a stall. So that means that you're trying to send another command on that buffer, but the buffer's already full, and so the buffer is like, no room for that. So I have to stop and actually process through the whole thing, have to flush everything out before I can process this new command. And what that's going to look like to you is that suddenly one of your commands, one of the commands you're sending to OpenGL is going to look like it takes a really long time for no reason in your profiling view. You're like, wow, that command was always perfectly fine, and now it's taking 40 milliseconds. And that's because you spilled the buffer and you triggered a sync flush. So really the only thing you can do here is try to amortize the cost of uploading across frames. So just try to limit what you do per frame. If you see these big stalls, you can have an intuition that you're probably or might be spilling that buffer and act accordingly. One note here is that when I talked about this with the Chrome GPU team, they said, yes, this is true for now. This is good information, but this is something that's subject to change in the future. So keep checking back in with this assumption. Hopefully this will get better. That buffer, this problem of causing sync flushes won't be a problem in the future, but for now, this is good advice. All right, so now let's talk about the close to the hardware type of part of the system. So what do you need to know about drivers? Really just that they're there, and that not all drivers are secure, not all drivers are stable for use with WebGL. And that means in order to keep people's browsing experiences secure and stable, that many or some drivers are blacklisted. So sometimes people running on a computer that is a computer and browser, perfectly capable of playing your game, will not be able to use WebGL because their drivers are blacklisted. And unfortunately, the only way to test whether the local machine is capable of running WebGL is by actually trying to create a context and seeing if it fails. So the first thing you do when you're making a WebGL application is make a WebGL context, and you really just have to try it, see if it works, and then handle accordingly. There's no sort of more elegant way than that. The other thing I mentioned is this almost native graphics layer engine, which in response to the fact that in general, DirectX rendering works better on Windows than OpenGL rendering, or rather, OpenGL drivers for Windows tend to be somewhat buggy or unstable. There's this layer called Angle, which will translate your OpenGL calls into DirectX before rendering on Windows only. Hopefully you never need to know about this. It's just sort of trivia, but it's good for you to know that it's there just in case. And then finally we have Swift Shader. Again, this is software rasterization. So if you have a system that's capable of running, capable of running your game, but for some reason their drivers don't work, then you might get Swift Shader. Swift Shader software rasterization. Now, this is just another case where you're going to have to be really proactive about judging the performance of the local machine, because of course software rasterization is going to be nowhere near as performant as hardware accelerated OpenGL. So you need to be really careful that you're catching these cases and testing the performance and degrading appropriately or informing the user appropriately. Again, you never had any guarantees about software rasterization or not. It could always have been a 10-year-old graphics card. Now you have software rasterization in the mix. That just hammers home that point a little bit harder. All right, so let's talk about your rendering loop for your game. So old-style JavaScript, the way you would do periodic function calls are with these two methods, set interval and set timeout. But the problem with those is that there's no way to tell the browser what you're doing. And again, much like we were seeing with the V8 case when we were talking about performant JavaScript, performant rendering in general, being performant in general, is about being able to inform the system what you're doing in specific terms so that it can optimize around you. Set interval and set timeout are not specific about what they're doing. They could be doing anything. We don't know that this is an animation, so the browser can't do anything to help you. And that's why they're bad ideas. Instead, there's this nice API in the HTML5 family of APIs called request animation frame. And this is a way to do periodic rendering in a way that tells the browser exactly what you mean. So request animation frame will try to call it 60 Hertz, and it'll adapt down sort of if you can't actually call it 60 Hertz. It'll never call faster than that, but it'll call slower if it needs to. If you because the request animation frame callback is always going to be sort of scaling its performance to how long your frames are taking, if you can't run at 60 hertz, then your frame rate's going to go a little jaggy because it's going to be based on how long one of the recent frames took. And so if you don't want your frame rate to wander, you need to clamp it to either 60 or 30. If you're trying to clamp your frame rate to 30, what you do is just the simplest thing possible. You're just going to manually skip frames by making a counter that counts up, and you render on even frames and not on odd frames, or whatever. So that's what you want to do if having a jaggy frame rate bothers you. And the other thing that request animation frame can do for you, because it knows that you are animating, is it can sort of feed Chrome's rendering pipeline with your data at a consistent rate. And it can adapt the work you do on the GPU and CPU to make sure that you're not just throwing a bunch of commands over the wall that you could never possibly render on the GPU, that you're not totally swamping everything. That's what request animation frame gives you. All right, so this is a typical game loop. You have, update, render, swap, update, render, swap. That's pretty normal, while true, do this. That's a game. This is the way it fits into Chrome. So you have request animation frame, which is your JavaScript code. You have composite, which happens, Chrome takes care of that. That's where everything is swooshed together and rendered on the screen, and then you have a swap as well. So that loop is going on if you have the main loop of your game in there. If you didn't have that, the browser would just go back to idle and sit idly. User input can also cause a screen dirty, which causes a composite, which causes a swap, which then either goes back to idle or goes back into your request animation frame loop. All right, so now let's talk about the life of a frame. So the way frames work in Chrome is that we have request animation frame calls. So first thing that's done is that your JavaScript in your request animation frame call is executed. And during that JavaScript, it'll kick off a bunch of calls that result in commands on the GPU. So you're going to kick off commands down that RPC buffer that are going to go onto this other rendering process. When all your JavaScript is completed and all your GPU work is completed, you have all the information you need, so you can composite the whole frame together, and you can do a swap. So that's the general cycle. You do your JavaScript callback, which kicks off your GPU work. When all that's done, you can composite, and then you just wait out the rest of the frame. If this is already your frame is nicely 16 milliseconds, is under 16 milliseconds rather, it'll just wait until the next call of request animation frame. So yes, it just keeps on like that. So in that diagram I showed you before about how all things fit together, one thing I left out is user input. So I want to talk a little bit about user input now. One really important thing you need to know is that while your main JavaScript thread is busy, input is queued. And that can introduce a lot of input latency into your code. So let me talk about how that actually works. So here we have a diagram similar to before. So it's sort of showing a series of frames. First you do your JavaScript work, then you do your GPU work, and you just keep doing that. If during my JavaScript work I get a bunch of mouse move events, I'm not going to hear them right away. I can't hear them while the main thread is busy, and they came in while the main thread is busy. Once the JavaScript execution is done, you're eligible to hear a mouse event. So here, in this case, I'm going to hear this most recent, freshest mouse click. Then during the next frame, now I've got a mouse event. Now I'm eligible during the next frame to process that mouse event. And then at the very end of the next frame, when everything's rendered, the results of that mouse input can get rendered. And so you can see, especially with this queuing delay, where if events come in while the main thread is busy, they just get queued up and you can't hear them until later. You can have a lot of input latency. The rule of thumb is that your input latency is going to be approximately twice your frame length. So if these are 16 millisecond frames, then the maximum input latency you can get, if you're unlucky, is 32 milliseconds, which is a hell of a lot of latency. But that's sort of the system that you live in, so you just have to be ready to deal with that. The other thing you can do to help yourself is to move work off the main thread. So moving work to the GPU is good. Moving work to web workers is good. Anything that helps you free up the main thread to be able to receive user input is good for you. All right, so one more thing to talk about user input is that one of the really important things that request animation frame does is it allows Chrome to schedule your work accordingly. So again, we see the same sort of simplified version of the diagram we've been looking at, where you have your work and then Chrome's work and then wait. Your work and then Chrome's work and then wait, and so on and so forth. This all makes perfect sense, nice repeating pattern. But when you have outside events, DOM events or timers or things going off that cause things at unexpected intervals, Chrome no longer has the ability to schedule those things. They just happened in on events. So in this case, on the slide, I got this on-click event. It required some work. That processing all would have fit in this frame nicely, but because Chrome didn't know about that work, it couldn't schedule it, which means that this frame is actually going to be delivered late. It's going to wait for that on-click event to complete. It's going to deliver the frame late, and then the next frame, frame n+1, is actually going to have a shorter time in which to execute. So what this means to you is that is essentially never do any work outside of request animation frame. If you want like a DOM-based HUD over your WebGL game, what you really want to be doing is buffering up all user input and then handling those user inputs in the request animation frame callback. You don't want to just handle them whenever they come in, because you have to think about how Chrome is actually scheduling the work. You have to give Chrome a chance to pack that work in nicely, which means that you have to actually do any processing you want to do inside the request animation frame callback. All right, so just in summary of what we've learned about living inside Chrome, first of all, throttle your upload per frame. Watch out for big performance stalls. Those are probably sync flushes, and they mean that you're uploading too much data at once, essentially. Your game lives inside Chrome, so you have to respect Chrome's natural rendering cycle and have to be prepared to give 2 to 4 milliseconds per frame to Chrome for all the compositing and swapping and finalizing that Chrome needs to do. So you don't actually have 16 milliseconds, you actually have 12. Hopefully it'll come in under 4, but you have to be prepared to give that much away. Never handle outside events directly. Never handle user events directly in events. Make sure you queue all the work you need to do up and handle it in RAF. All the work you do should be inside your request animation frame callback if you want Chrome to be able to schedule it nicely. And then if you're concerned about input latency, if that's a big deal for you, then the best thing you can do there is move work off your main thread. Move it to the GPU, move it to web workers, whatever. Just know that the input is blocked or queued while the main thread is busy, and that's just going to imply some input latency for you. So in general, all this sort of amounts to be aware of what Chrome is doing and how you fit inside it, and try to sort of work with that. Whew. All right, so we've talked about how to write fast JavaScript. We've talked about how to make that JavaScript work well inside of Chrome. And now, just in the short time I have left, I'm going to talk about the developer tools you need to sort of check how well you're doing. All right, so first of all, just be aware that Chrome's got all these handy-dandy flags. So you can type about and then a number of things different into Chrome to get some cool stats. So there's about flags, which has a lot of graphics options, including an FPS counter, which I essentially just perpetually leave on. There's about memory, which shows you exactly what's going on with memory in Chrome. It's a very in-depth, detailed view. There's about GPU, which is useful for figuring out what Chrome thinks your GPU stats are. Or if you're taking bug reports from external people, it's really nice to get them to dump that data and give it to you. So these are all tools you should be aware of. Then we have the Chrome developer tools. So the Chrome developer tools are really, really useful. They were designed or have been used most often on web pages. They're really, really great for web pages. They're also good for games, but they've been optimized around that case. So for instance, the CPU profiler only takes samples every 1 or 2 milliseconds. So it's a lot less resolution than you would want, but they're really good for something. So how you get to the developer tools, there's a wrench icon up in the upper right hand of Chrome. Then you go to the Tools menu, go to Developer Tools. And the things you should be aware of there are the timeline view, which completely rocks for trying to see how your resource loads are going. That's the thing that I find it most useful for, is seeing where resource requests were made and how long they took. There's the CPU profiler, which will, standard profiler. Again, resolution a little low, but it still can be really useful. And then there's the heap profiler, which is a super useful, in-depth look at exactly where all your memory is. So those are the tools that are most important, I think, of the Chrome developer tools for game developers. And then there's about tracing. So about tracing is the heaviest weight tool you should be aware of in Chrome if you're actually trying to debug a game. So this view that's on the slide, pretty confusing the first time you look at it. Every one of these colored lines, colored vertical lines, represents a function call that's instrumented. And so this actually gives you a list of all the instrumented function calls on every Chrome process, so for every open tab, as well as calls for the GPU. So this is the tool you're going to look at if you're going to want to see how your CPU work and your GPU work relate. This is what's going to be useful. So if you zoom way in on that view I just showed you, you can see that each one of those colored boxes, actually you can see a function name in it. And that function name data is really raw. Again, it's right out of the source code. So if you don't know what, draw layers means, then in this particular context, then, that's too bad. But you can kind of look at the function names and make educated guesses about what they mean. And then the really useful thing you can do with this is that from JavaScript, you can add console.time and console.timeEnd tags with your own string tag. And that will create a colored box in this view, just like all the other function calls, that will manually instrument a function call for you. And you can see exactly where your function call happened within your frame. So this is a tool you definitely want to be aware of. And finally, I know I mentioned this in the section about JavaScript, but you really should be checking your code with V8 flags. Unfortunately, this information about what JavaScript is fast and slow isn't surfaced really well to the user. It's all sort of at the command line, but it's very important information. And so I also put up here exactly how to run this for a Mac. It's not really friendly to being on a slide, but I wanted people who had these slides after the fact as reference to be able to refer to it. So that's actually a call you can cut and paste into your Mac to make this happen. And then finally, there's WebGL Inspector. So WebGL Inspector is an open source Chrome extension which sort of patterns itself after Pix or one of these other heavyweight graphics debugging tools that people in the games industry especially are really fond of. So if you want to step through draw calls or see exactly how your textures are bound or something like that, WebGL Inspector is going to be very very useful to you. So you should definitely check that out. And then finally, one more note before I'm out of time. I just want to stress that we really want feedback. It's not at all annoying or unwelcome to file bugs. It's really welcome. I really look forward to working with teams that are verbose about what they want, and they file bugs in Chrome, and they sort of squawk a lot about what's working and what's not working. So please, when you find things that don't work in Chrome, or things you'd like to work better, or features you want, please log things into crbug.com. That's the Chrome bug database. Or if there are features you want in WebGL, or in any of the HTML5 specifications, please go to those mailing lists and talk about what you need and what your experience is. The community is not so large that you can't make a difference. Really, the decisions are made by the people who show up, and you are really capable of influencing what actually gets done. So please email those mailing lists, file bugs. Everybody really wants to hear from you. All right, and that's it. Thank you very much.